This is a very interesting problem. We want to determine whether the function x to the fourth minus y cubed has any absolute extrema on R squared. When we're looking for absolute extrema, we cannot directly apply the second derivative test, which ensures the existence of local extrema, but it's not totally useless either, and we're going to explain why in a second. We also need to understand that such a function is not guaranteed to have an absolute minimum and an absolute maximum because its domain of definition is not the kind of domain that ensures something like that. In general, when you have a domain of definition that it's bounded and contains its own boundary, we call that compact, then a continuous function always has a minimum and a maximum, but not in this case. However, here we're going to use a very simple piece of logic, which is that if that a global extremum is also a local extremum, but not the other way around. So hence a critical point. So if there is, we could have also said that right from the beginning. We don't need to actually use the local extrema as a bridge between global extrema and critical points. However, what we wrote is not incorrect either. The bottom line is that an absolute extremum will still be a critical point. So we can start by looking for critical points and then ask ourselves how to understand whether a given critical point that we found or critical point that we found is or not an extremum. So let's see. Let's first of all find the critical point. So we begin. So f sub x will be equal to 4x cubed, and f sub y will be equal to minus 3y squared. And if we set them equal to 0, then the only thing that we get from here is x equals 0 and y equals 0. So in other words, 0, 0 is the only critical point. And hence, what we need to answer is the following question. Is 0, 0 a local minimum? I'm sorry, a global minimum, meaning an absolute. Or we can even drop both adjectives, or a global maximum. So first of all, to answer this question, we cannot use the second derivative test. And we cannot use it for more than one reason. First of all, the second derivative test does not tell us anything about global extrema. Secondly, it's not even applicable here. If we find the second, the determinant, we will see that it's 0. So it's useless for two reasons here. What we have to ask ourselves and see if we can answer this question is f of 0, 0, which is actually 0, the largest or the smallest possible output for f of xy. And this is where things are pretty straightforward, because now we can look at our function. This is something that doesn't even need any calculus knowledge or anything else. You just look at this function and ask yourselves, does this function assume an output greater than 0? If it does, it's not a global minimum. Does it assume an output which is less than 0? If it does, then it's not a global maximum. I'm sorry, maybe I said it the other way around. If it assumes an output which is greater than 0, then 0 is not a global minimum. I'm sorry, global maximum. If it assumes an output which is less than 0, then it's not a global minimum. Okay, so does it assume some output which is greater than 0? Of course it does. I mean, we can just look at it. For example, f of 1 comma 0 is 1 which is greater than 0, hence 0, 0 is not a global maximum. Okay, it's as simple as this. And the idea is that sometimes math is just about reasoning, simple reasoning. It doesn't have to be about knowing formulas or theorems. And now ask yourselves the same question. Can you cook up a negative number? And I think you can easily see that, yeah, I mean, it's not that hard. Just take f of 0, 1. That's going to be negative 1, which is less than 0. Hence, 0, 0 is not a global minimum. So 0, 0 is not a global extremum. And since that was the only possible global extremum that we have, the answer to the initial question is that f does not have global extrema, absolute extrema. Again, absolute and global is the same thing here. And that completely answers our initial question. And that's all. Thanks for watching.